this lesson is about something called stoichiometry. It's the math we use in chemistry that requires a balanced chemical equation. As we'll learn in this lesson, we need a balanced chemical equation to be able to create the step in stoichiometry called the Molar Ratio step. So this is what the Oxford Dictionary says is stoichiometry: the relationship between relative quantities of substances taking part in a reaction or forming a compound to typically a ratio of whole integers. Well,
stoichiometry.
This is the definition that I usually use. The math and chemistry that requires a balanced chemical equation. These relative quantities in the dictionary definition, that's the coefficients in a balanced chemical equation. So here's the problem we're going to start with. If 2 moles of aluminum are reacted with a solution containing an excess of copper 2 sulfate, how many moles of copper metal will be formed? Alright, so I chose to do this particular problem because I had this email this weekend, which was kind of cool. So I answer questions on this service called Ask a Scientist. I'm not the only person. There's lots of people around the country that do this, but I get a lot of questions from high school students and high school teachers and elementary school teachers and elementary students sometimes. And they were asking about this reaction, this thing they were doing. They were just trying to crystallize, which just means dry it out. They had a solution containing copper sulfate. They were trying to dry it out, and they were doing it on an aluminum pie pan. And they couldn't figure out where this orange sort of stuff come in there. How did I get this copper-looking stuff around the corners? Well, that was a single replacement reaction. We just did single replacement reactions. But if you kind of know a little about chemistry, you can figure out what's going on. So I decided to use this equation as an example here, okay? Because this is talking about this particular single replacement reaction where aluminum is replacing copper in a compound. We have aluminum, and aluminum is a metal, and almost all metals are what physical state? Solid. So we got aluminum, that's a solid. And what physical state is this copper 2 sulfate going to be in? Not liquid. Liquid means that it is a liquid. AQ means it's dissolved in water. Okay? Now let me tell you something about when I say solution, because this is important for you to know. That unless you're told otherwise, you can always assume solution means dissolved in water. If any solution is anything other than dissolved in water, then the problem or something should tell you it's dissolved in something else. Okay, so that's because it's so ubiquitous. Things are dissolved in water so much that when we say solution, that's what we mean. Okay. Now, if it's dissolved in water, we're going to call it AQ. So copper and sulfate then are dissolved in water. But how do we balance this formula? What do we got to do to balance the formula? Well, that's for the products, predicting the products. What do we do to balance this formula here? Got to find it's about the electrons. Oxidation numbers, the charge numbers we're looking for. Okay, so what's the charge that we'll assign to copper? It's right here, folks. Look, don't go looking at your references. This is right here. 2 plus. Okay. Now you can look at your references and tell me, if you don't already know, what's the charge on a sulfate polyatomic ion? Okay. So one of these and one of these will balance out. What we want is a compound that has no charge, and a 2 plus and a 1 plus balance each other out, wipes it out. We have a 0 charge overall. Okay, that's what we want. So this is AQ because it's dissolved in water. Now, on the other side of the equation, this is where we go about predicting. Okay? And we already said we're going to form something on the other side. We can go and write that down from what it says in the problem. We could go and look at the activity series and figure out what we're going to make, if we're going to make anything. But it says right here we're going to have. Okay, we're going to have copper. All right? So what's the other thing we're going to have on this side? Well, first of all, we've got to classify the equation. What kind of equation do we have here? What kind of reaction do we have here? Single displacement. So what happens in a single displacement reaction? Well, there's some switching going on. Things that are like, something that the element by itself is like in the compound, it displaces. Okay? So aluminum is going to displace the copper. That's why copper is by itself. So what do I put together over here then? Aluminum and sulfur, or sulfate. Okay. Now, what do we do to balance this one? Okay, so what's the oxidation number of aluminum? Okay, and the charge number we said for sulfate is 2 negative. So, what do we got to do to balance this equation? Or this formula, rather.
2 aluminum and 3 sulfate.
Good, 2 aluminums and 3 sulfates. So when we write it as a formula, then I need a subscript 2 here, but I can't just put a subscript 3 here. What do I need? Parentheses to show that I have 3 sulfates. Now, what's the physical state for the aluminum sulfate? What's the physical state for the aluminum sulfate? Where do you look to find the physical state for this? Solubility rules, because there's water around and this is an ionic compound, we're going to look at the solubility rules to find out what physical state it's going to be in. And what physical state will it be in? It says here that sulfates are soluble. There's some exceptions, but is aluminum one of the exceptions? No. So what physical state? Aqueous. Okay? All right. And now that we've figured out the formulas, we've balanced the formulas, we have to leave them alone. We can't change any of the numbers in the formula. We can only balance the equation using coefficients. So please, balance the equation. Use the process you've been taught and balance this equation. All right, so you write first the number of each atom you have in both sides of the equation. So on this side of the equation, I'm sorry, Fred. Okay. So on the left side of the equation, we have 1 aluminum, 1 copper, 1 sulfur, and 4 oxygens. And on the right side of the equation, you've got 2 aluminums, 1 copper, 3 sulfurs. That's because this sulfate ion, this polyatomic ion, is inside of parentheses, and the 3 outside is multiplying everything inside. That's 3 sulfurs, but 12 oxygens. And so what we want to do is try to get everything the same on both sides. Since I have 2 aluminums on the right, to get 2 on the left, I'll put a coefficient 2. You can't put anything in the formulas. You can only use coefficients. That's going to change the number of aluminums to 2. Go down here to sulfur. We're going to save oxygen for last. Always save oxygen as the last thing you balance. You don't have to write it last, but always save it for last to balance. I've got 3 sulfurs on the right. To get 3 on the left, I can't do anything to the formula. I can't put anything inside the formula. I have to put only coefficients in front. So I put a 3 here, which changes the number of coppers, sulfurs, and oxygens. We now have 3 coppers and 3 sulfurs and 3 times 4 or 12 oxygens, and that'll balance the, well, no, we've got to go back over here and put a 3 here to balance the copper. Okay? So that's a balanced equation. Now, that's the first thing you have to do. Before you can solve a problem like this, where you go from one chemical species, in this case the aluminum, to another chemical species, in this case the copper, before you can go from one chemical species to another, you have to have a balanced chemical equation. You cannot solve this problem in any other manner. All right. Now, what you learned in Unit 1 was when you're doing problems like this, where there's a conversion of some kind involved, you have to start by putting the starting amount over 1. In this problem, I don't think you can be confused about what the starting amount is. There's only one starting amount in there. Okay? And that's 2 moles of aluminum. We'll put that over 1. Now, in Unit 1, we learned to use what are called conversion units. Now, we're not going to be using a conversion unit per se. We have a conversion ratio. We are converting using a ratio, but it's not a unit, okay, because the two parts of this do not equal 1. But the reason we have a balanced equation is because this is where we're going to get this conversion to go from one chemical species to another, called a conversion ratio. Or even more technically than that, more specifically than that, it's called a molar ratio. A molar ratio is a ratio of moles you get from a balanced chemical equation. A molar ratio is a ratio of moles you get from a balanced chemical equation. Molar ratio. Now, with a chemical equation, what we're saying here with these coefficients in front of the numbers we put in here and the implied 1 over here next to the aluminum sulfate, this says we have one of atom, in this case, of aluminum, or 2 atoms of aluminum here. Okay, we have 3 of this stuff. Now, this is a formula unit. Remember when we talked about the structure of ionic compounds, we said most of the time they form these really large crystals where you've got millions of coppers and sulfates that are joined together in one structure. But in order to use this in a chemical equation, we use this as a formula unit. It's like we had just one copper, 2, and one sulfate bonded together. That doesn't really happen, but that's the way we treat it in a chemical equation. We're saying there are 3 formula units, okay? So when we have an ionic compound, we refer to the formula as being the formula unit, okay? When we have an ionic compound, we refer to the formula, when we're using it like this in a balanced equation, as the formula unit, okay? It's the individual parts that make up the whole of a crystal, okay? You have to have one copper and one sulfur repeated over and over and over millions of times to get a crystal of copper sulfate. In this case, we have 3 formula units, okay? So we're going from moles of aluminum here to moles of copper. And in a balanced equation, this would be 3 atoms of aluminum and 3 atoms of copper. But what if we were to multiply both sides of the equation by the same number? Would the equation still be equal? Yeah. It's just like any other equation in math. If you multiply both sides by the same thing, the 2 sides of the equality are still equal. No, it just means this coefficient 3 here in front is where we get 3 formula units. Okay? Yeah, 3 copper sulfate formula units. This would be 3 atoms because that's the structural particle that makes up this metal. This would be 3 atoms because atoms are the structural particles that make up this metal. But these 2 here, these are formula units. So we have 3 formula units and 1 formula unit. Okay? All right. Now, all you have to do when you're converting from one molar amount of something to another molar amount of a different species is use those coefficients. Because what you're essentially doing is multiplying these 2 atoms and these 3 atoms by Avogadro's number. Okay? Avogadro's number is 6.02 times 10 to the 23rd particles of anything equals 1 mole. And if we multiply this by Avogadro's number, how many moles do we have? 2 moles. If we multiply this by Avogadro's number, how many moles do we have? 3 moles. Because Avogadro's number means that's a mole. A mole is 6.02 times 10 to the 23rd particles of anything. Okay? All right, well, that's what we're going to be using down here. So this actually represents either atoms or formula units or molecules. If we had molecules, we don't have any here, but if we had those, it'd be molecules. But when we use it in the equation down here, in the stoichiometry equation, in the dimensional analysis we're going to be putting together, this becomes moles because we just multiplied everything by Avogadro's number. All right, so down here, instead of saying 3Al, it's going to be 2Al, it's going to be 2 moles of aluminum. And on the top, we're going to put the thing we're looking for here, copper metal, and that's 3 moles of copper. Okay? Well, remembering, I hope you remember from Unit 1, dimensional analysis, how do we simplify this problem?
You eliminate aluminum and moles.
That's right. Now, what we have left then, in this dimensional analysis process, we've analyzed the dimensions of measurement of moles here. What we've done in this dimensional analysis process is to see that after everything's canceled, we're left with moles of copper, and that's what the problem's asking you to find, moles of copper. So all you have to do now is the math. Okay? If you can do it in your head, do it in your head. Otherwise, get out your calculator and solve the problem.
You know what I can. But I got it.
Well, put it in your calculator if you're confused. But you know what? It's really simple. 2 is canceled by 2, isn't it? But we have to keep up with the significant digits. This number had 3 digits. Both of these are counting numbers. They don't count in the process of figuring out significant digits. So you have to have as many digits as you have in this number. Okay, now, so that's all from Unit 1. All right, so let's give you a practice problem to do now. Just you and or learning partners around you. So this problem states, if 5.25 moles of copper 2 sulfate in a solution is mixed with a solution containing more than enough, which means in excess, strontium chloride, how much solid will be produced? So you've got to figure out what the starting chemicals are, figure out what the ending chemicals are. Starting chemicals are the reactants or reagents, ending chemicals are the products. What the ending chemicals are to figure out what the solid's going to be. So you have to know the physical state to even figure this out. Okay, and this is something you were taught in the last unit. So we're reviewing, in a sense, this, because you're going to need it in this unit too. So I'm going to give you a chance to solve this. You may do so alone if you want to, or use someone near you, or more than one person near you, getting a learning partner, getting a learning group together. But get it done. You don't have permission to sit and do nothing or chat about the weekend. Okay, you have permission only to do this problem. Alright, so to solve this problem then, we need to first balance the equation, and so we need to figure out from the problem what the chemical species are that are reacting together. We have a copper 2 sulfate. Copper 2 means this copper ion has a 2+ charge. Sulfate is a polyatomic ion. You look that up on your common ions list, and the formula for sulfate is SO subscript 4 with a 2 negative charge. So when you put together copper 2, which has a 2+ charge, and sulfate with a 2 negative charge, that formula is CuSO4. And we're going to mix that with a solution that contains excess strontium chloride. Strontium is Sr. Chloride, that IDE ending, means you have a monoatomic anion. The IDE ending in an ionic compound means it's a monoatomic ion. And we know it's ionic because we have a metal combining with a nonmetal. So strontium has a 2+ charge. Chloride has a 1 negative charge. So this formula needs to be Cl subscript 2 to have charge balanced compounds. Then you use your solubility rules to figure out the physical states. Solubility rules say that sulfates are almost always soluble, and there are some exceptions, but not when it's combined with copper. So if it's aqueous, and we already said it's mixed in a solution, so that must be aqueous. If it says it's soluble and there's water around, it's going to be aqueous. Solubility rules also say that chlorides are almost always soluble, and while there are some exceptions, strontium is not one of the exceptions, so that's aqueous. All right, we're going to put those together, and we're going to figure out what kind of product formulas we're going to have. These are reactants on this side of the equation, on the left side. They're also sometimes called reagents. When you actually have chemicals you're using in the lab, we call them reagents. And so what you have to first predict or classify what kind of equation you have. And that was in the last unit. It has to be double replacement because I have an ionic compound in 2 parts and another ionic compound in 2 parts. And so they switch parts. The front part of this has to go with the back part of this. The front part of this has to go with the back part of this. The positive part has to go with the negative part. The positive part has to go with the negative part. So copper is going to, if there's going to be a reaction, copper has to join up with chlorine, and strontium has to join up with sulfate. All right, so copper over here was a 2+. This copper with the Roman numeral 2 in the name tells you it had a 2+ charge. And unless you know otherwise, unless there's some reason to believe, reasonable reason to believe, that it's changed its charge, you assume it has the same charge on the right-hand side. So this is a 2+. Chloride, we said over here, was a 1-. So to have a compound that is neutrally balanced, that is the charges wipe each other out, I need 2 chlorines with a 1- charge to wipe out the 2+ charge on the copper. And of course, we said that chlorides are going to be soluble if there's water around, or they're soluble whether there's water around or not, but they're going to be aqueous. That's going to be aqueous because it is soluble and water's around. All right, strontium has a 2+ charge. Sulfate has a 2- charge. So those charges automatically sort of wipe each other out. So we only need 1 and 1 of these. Then you look up in the solubility rules, and why don't we just bring that out and look at that real quick. It says that sulfates are mostly soluble. So there's water around, it would be soluble unless it is bonded with, among other things, strontium. So since most sulfates are soluble, but not when bonded with strontium, this is a solid. Okay, so now we balance the formulas. And when we balance the equation now, we have to leave the formulas alone. We cannot change the numbers in the formulas. And so we're going to do an atom inventory to balance the equation. We write down all of our elements: copper and sulfur, oxygen, strontium, and chlorine. Count all the atoms we have on the left-hand side. So everything over on this side of the equation is going to go in here. Everything on the right-hand side of the equation is going to go in here. And so this equation is balanced. Now you might be able to do this in your head, but I want you to put it down in an atom inventory, even if it is balanced, so that you can clearly see and I can clearly see that it is balanced or not. So now that we have it balanced, we're ready to solve the stoichiometry. Without a balanced equation, you cannot do stoichiometry. So we're going to start with the starting amount. And the starting amount, it says, is 5.25 moles of copper 2 sulfate. So 5.25 moles of copper 2 sulfate. And we put the starting amount over 1. And there are times when you don't put it over 1, but for almost all of the stuff we do in here, starting amounts in stoichiometry, and in fact in some other kinds of problems, but starting amounts go over 1. Then we're going to build a conversion factor of some kind. Now this is not a conversion unit. In Unit 1, the Unit 1 study in this class, the Unit 1 instructional unit in this class, we learned to do dimensional analysis. We learned how to set up a conversion unit where two things are equal and you put them in a fraction. These things we're going to put here are not actually equal, so we can't really call it a conversion unit, and it's called a molar ratio because it's a ratio of moles. And so we're going to look at the balanced equation. We're going to see all we have are coefficients of 1s. They're implied 1s here in front of each of the chemical species. So all of our molar ratio is going to be 1 to 1. Okay, it's really pretty simple here. We want to have matching units and species on the bottom here. We're going to take a look at our starting amount and look at the units and species in the starting amount and construct this conversion so that the matching units and species are on the bottom here. And so since this is going to be moles, we're going to take each one of these implied number 1s, multiply them by Avogadro's number in our head, and we get 1 mole and 1 mole and 1 mole and 1 mole. So here we're going to take this 1 mole of copper 2 sulfate to match these units and species. We're going to put it on the bottom. 1 mole of copper 2 sulfate. and then we're going to find the thing we're looking for. What is the chemical species we're trying to get to? And this chemical species we're trying to get to is the solid. Well, there's the solid. When we figured out what the physical states are using those solubility rules, we found that was a solid. So we're going to put moles, or 1 mole of strontium sulfate on the top here. Okay? And now, going back and hearkening back to Unit 1, where we learned to use dimensional analysis, we have matching units here and here. Those cancel. If it's on the top and bottom, they cancel. Can't cancel them if they're on the top. They're both on the top. But if I have a unit that's the same as a unit on the bottom, they cancel out. If I have a species the same as one on the bottom, they cancel out. Okay? And so now we're ready to solve the problem. This is a pretty simple problem, because 1 times that and divided by that is simply going to be the same number, 5.25. But we don't have any moles left here or here. Don't have any copper sulfate here or here. What we have left is moles of strontium sulfate. And so that is what the question is asking for. Whenever you finish your problem, always go back and look at the problem and make sure you're answering the question it's asking you to answer. Okay? And it says, how much solid? Well, that's the solid, so this is the amount here. And moles, if you don't remember, is the SI, or System of International Units, measurement of the amount of substance. And you should have known that from your mole project. All right, I want to give you a new problem now. It's going to be kind of similar to this problem. I'm going to word it just slightly different. And what we're going to do now is to add something to this process, okay? Okay, and what we're going to find out now is how to do something called calculating molar mass. We're going to be learning to calculate molar mass here. All I want to do is reword this problem here to replace moles with the word grams, with the units of grams here. So we're going to change this from being moles of copper 2 sulfate to grams of copper 2 sulfate. And instead of finding how much in moles of the product, we're going to find how many grams of the product, okay? So let's rewrite that problem then.
You're making my hair fall out. And that's a whole lot of help. You made all mine fall out. That's why I said it.
All right, so I've worded almost exactly the same this second problem. But now instead of starting with moles, we're starting with the same numerical value, but now we have grams, okay? And instead of finding just how much solid, I specified we need to find the mass of the solid that we produce, okay? So we have this balanced equation already. We did that previously. We balanced this equation. We've got that ready, okay? It's still stoichiometry. But now I've got to go starting with the mass of copper 2 sulfate, and end up with the mass of the solid, which we previously identified as strontium sulfate. Okay? Now, we're going to take a step back from that just for a minute. And the thing that we don't have right now, is how to calculate the conversion that's going to get us 2 moles. Here's the thing. I can't go from one chemical species to another without things in moles. It's not possible. I have to have a balanced equation with coefficients and produce a molar ratio. So I first got to get this mass of copper 2 sulfate into units of moles. And for that, we're going to do what we learned to do in Unit 1, which is to do a conversion unit with something we call molar mass. We're going to first learn how to calculate molar mass. Now for that, we're going to need 2 different molar masses. I'm going to do one for you. You're going to be expected to do the other for yourself when I show you how. So I'm going to start with the starting amounts molar mass, the starting species molar mass. Copper 2 sulfate, that's this chemical species right here in the equation. And to calculate molar mass, to get the conversion unit we need to go from this mass here to moles of that same species, molar mass is what I'm calculating. I'm going to list all the atoms in this formula here. Copper, and I'm going to list them vertically, copper and sulfur and oxygen. I'm listing them vertically in the same way that we listed them when we're doing an atom inventory. But we're not doing an atom inventory. All right, we're doing something else here. Now, I'm going to write a colon next to each of those symbols. And then I'm going to go to my periodic table. And I'm going to look at the atomic masses for each of these elements. Now, let me give you a definition for molar mass. Okay? Let me give you a definition for molar mass. Molar mass is the sum of all the atomic masses of all the atoms in a formula in units of grams. Molar mass is the sum of all the atomic masses of all the atoms in a formula in units of grams. So, in copper 2 sulfate, there are 4 oxygens. So I could add up the atomic mass of copper, the atomic mass of sulfur, and I could add 4 times the atomic mass of oxygen, because it's the sum of all of them. And there are 4 atoms in this formula unit. Okay? Or I could take that atomic mass right there and multiply it by 4, which is a little bit faster, don't you think? That's what multiplication is, by the way. It's another form of addition. All right. So I like to do it with multiplication. That's what I expect you to do, because it does speed things up when we have more complex formulas. So we're going to take the atomic mass of copper, 63.546. So go to your periodic table and find the atomic mass for sulfur and the atomic mass for oxygen and write those down here. All right, so in the formula we said we've got 4 oxygens. So I could write oxygen down 4 times, but I prefer to multiply that. So I'm going to multiply each of these by the number of them in the formula. Okay? Now the numbers that result over here are going to be added together. So keep all of your digits aligned vertically so you can keep up with significant digits here. Oh, I got to multiply that by 4, don't I? Now then, when I add all these together, it will be the same thing as adding this and this and this 4 times. I just multiplied it to kind of speed it up a bit. Okay? Now notice we've got an empty slot twice over this 6. So if you remember your significant digits from Unit 1, we're going to have to round off a number on the end here. I have no idea why I put 2 decimals there. All right, so we add these together. We've got a 6 on the end that has to be rounded off because it's added to empty slots. We don't know what they were going to be. We round them off. This 8 becomes a 9 because the 6 is 5 or above. We get grams then of copper sulfate. Okay, now listen. When we said the definition of molar mass is the sum of all the atomic masses of all the atoms in the formula in grams. That's the atomic mass. However, in order to use it as a conversion unit, you've got to know what it's equal to. And that is equal to 1 mole of that same thing. That's why it's called molar mass. This is equal to 1 mole of copper sulfate. And so for me in this class, it is required that you write this equality statement when you get the molar mass done. Okay? Doesn't matter where you write it equal to. You set beside, under, whatever works for you. Okay, there you go. All right, now we already have a balanced equation up here. We now have a molar mass. we're ready to start doing some calculations. Okay? All right. So we're going to start with our starting amount and put that over 1, just like we did before.
You need to fix your clock. You're an hour ahead. Because we just went an hour back.
All right. Now, from Unit 1, you know, or should know, how to build a conversion unit from this equality statement. I'm going to look at the starting amount and see that I've got units of grams and a species copper sulfate. So I'm going to choose the side of this equality statement that matches those units and species and put that side on the bottom.
Wait, so you're going to choose the equality statement that matches what? Oh, because the unit. They'll cancel out.
What?
5 times, how do you do the math?
What?
5 times 1.
Well, just hold on. We'll talk about that in a moment. Okay? Now then, when you put that molar ratio step in there and cancel units and species, you are now at the point where you have moles of strontium sulfate, because you canceled everything but moles of strontium sulfate. Okay? What you have to do in the final step is to calculate the molar mass of strontium chloride. I'm sorry, yeah, strontium sulfate. Calculate the molar mass of strontium sulfate, build a last conversion unit, and put everything together to solve for the final problem, which is the final thing, which is the mass of strontium sulfate. So you're going to put in your molar ratio step here, and when you cancel out units and species, you'll have only moles of strontium sulfate. Then you're going to convert that to grams. But to go from moles to grams, you've got to have a molar mass calculation like this one, only that's going to be the molar mass calculation for strontium sulfate. A whole nother molar mass calculation to get another equality statement to get the final answer. Okay? Now listen, last thing I'm going to tell you, and then this is your homework, and then we're going to let people do their post-lab. All right? Now listen. Whenever you get everything set up, molar ratio step, molar mass step. Okay? When you get all that set up and you cancel all your units and species, remember, you multiply everything across the top. Hit equals. Divide by one thing on the bottom that you need to divide by, hit equals. Divide by another thing on the bottom you need to divide by, hit equals. Okay? So you multiply everything across the top in one step, but dividing on the bottom, you've got to do in separate steps. Multiply across the top, hit equals, or enter. Divide by one thing on the bottom, hit equals or enter. Divide by another thing on the bottom, hit equals or enter. If there's a third thing, divide by the third thing on the bottom, hit equals or enter. Does that make sense?
What are you talking about?
We learned this in Unit 1.